Hello, everybody. Welcome to this session on learning mathematics through concepts and examples. Today, we are going to work on polynomial functions and equations, and we are going to explore this concept using some examples. So big goal for this quick lesson are you should be able to, describe the end behavior of the graph of polynomial functions. That is, if the polynomial function is given, okay, if the equation is given, you should be able to describe the end behavior of the graph of those functions. Next, you should be able to find the intercepts on the graph of polynomial function. And finally, you're going to learn how to solve the polynomial equations of degree 3 and 4 when one or two of the roots are given. So first example here, determine the end behavior of the graph of the polynomial functions given here in part A and B. So here you can see in part A, we have P of x equal to negative 3x to the 5 plus 26x squared minus 5. So in part A, what we can see is the leading coefficient. So in order to determine the end behavior, first of all, in order to determine the end behavior of any polynomial function, we look at the leading coefficient and the degree. So here, the leading coefficient, you can see here, if you go here, you can see that the leading coefficient is negative. Let me write negative like that. Okay, that's my way of writing negative. And then next thing we look at is the highest degree, or the degree of the polynomial. Degree of this polynomial is, you can see that the highest power of x in this equation or in this function is 5. So the degree is odd. So we look at two things. We look at the leading coefficient. We'll try to find whether it is positive or negative. And then we look at the degree, whether the degree is even or odd. In this case, it is odd. So if the degree is odd, always remember that the end behavior, in order to describe the end behavior, what we know is if the degree is odd, one end of the graph will go up, whereas the other end will go down. Okay, so there will be two direction there. And when we have negative, basically what happened is, let me show you quickly here. If this is the case, the left end of the graph will go up. Okay, left end of the graph will go up, and then the right end of the graph will go down. Okay, one more time. If the degree is odd, the end of the graph will go in opposite direction. So if one goes up, the other one will go down. But if it is negative, then we know that the left end will go up. That means the right end will go down. And this is one way of showing the end behavior. Sometimes in your textbook, it may be written like this: limit as x approaches to negative infinity, that is towards the left end, this function p of x, it goes up. It goes to all the way to positive infinity. So this is equal to positive infinity. And the right side, similarly, limit as x approaches to positive infinity, all the way to the right of the number line. Okay, if you go there, you'll see that the function will actually go down. It goes down. That means this will approach to negative infinity. So you can describe the end behavior either using the arrow diagram like this, or you can also write using the limits like this. Okay, and you can always verify your work using the graph. It's always easy to verify the work. So if you use your graphing technology and try to sketch the graph, you can clearly see the graph of this function and the behavior. So for example, here I have the graph. Okay, let me make it a little small. Okay, there we go. You can clearly see that the left end of the graph, this one, the graph that is drawn here, is the graph of this function. Okay, this is the graph of your first function, which is given here, p of x equal to this one. You can see that the left end of the graph goes up, as I described here, and the right end of the graph goes down, as I described. And also remember, in the fifth degree, okay, because it is a degree 5, that is the only reason why the left end will go. It's a degree 5. That's why the left end goes up and right end goes down, the opposite direction. Okay, and because it is negative, the left end goes up. If the leading coefficient was positive, the left end will go down. So that is something you need to remember in order to describe the end behavior. So always you can sketch the graph quickly and then try to verify. So this one is the graph for part A. Now let's look at part B. We can follow the same procedure. So for part B, you can see that the leading coefficient for this one, the leading coefficient is also negative. So like in A, so I can say leading coefficient is negative. And if you look at the degree, the highest power of x is 6. So it is even degree. So degree is even. Degree is even. That's an even degree. So what happened is, remember, if the degree is even, both ends of the graph will go in same direction. Left and right end, they will either go up or both will go down. Okay, they'll go in same direction. Since we have negative, if it was positive, both end will go up. But here we have negative, meaning of that is both end will go down. So the left end will go down like this and right end will also go down like that. That means if we want to describe this using limit, it will be like this. Limit as x approaches to either positive infinity or negative infinity, the polynomial function always goes to negative infinity. Okay, that's how we describe the end behavior. We can also verify this using graph. So you can use your graphing technology, your TI-84 calculator, or maybe you can use Desmos or some other online software to quickly verify this. Here is my graph for the second part. Okay, you can see this is my graph for second part, part B. You can see here, the left end of the graph goes down and also right end of the graph goes down. Okay, so one more time, in order to determine the end behavior of polynomial function, we look at two things. We look at the leading coefficient and degree. Okay, in case of odd degree, the end of the graph will go in opposite direction. If it is positive, left end will go down and right end will go up. If it is negative, left end goes up and right end goes down. Similarly, for the even degree, if the degree is even, both ends of the graph will go in same direction. If the leading coefficient is positive, both ends will go up. But if the leading coefficient is negative, both ends will go down. Okay, that is our first example where we try to describe the end behavior of the graph of polynomial function. Now we are going to move on to next example. Okay, here is the next example. Let's see what is this one asking us. Okay, if f of x equal to 3x cubed plus 8x squared plus 3x minus 2 has one real x-intercept at x equal to -1. Okay, here we are talking about one real x-intercept at x equal to -1. When we say real, the graph will actually cut the x-axis and it crosses the x-axis at x equal to -1. So the intercept will be, okay, x-intercept will be -1, 0. X-intercept is -1, 0. That is when you plug in -1 into this function, the result will be 0. That is the meaning, okay? And we also call the 0 of the polynomial. That means when you plug in that value, when you plug in this one into this, the result will be 0. Or if we divide this polynomial using this -1, okay, if you do the synthetic division, then you'll see that the remainder will be 0. Okay, first part is describe the end behavior. So as I told you before, in order to describe the end behavior, we look at two things. Okay, we look at two things. The first one is we look at the leading coefficient. You can see leading coefficient is positive. Okay, leading coefficient is positive. And then the degree, you can see the highest power of x is 3, so the degree is odd. Okay, degree of this polynomial is odd. So what is the meaning of that? We know that if the degree is odd, one end of the graph will go up, whereas the other end will go down. Because it is positive, the left end will go down and the right end will go up. So that is the end behavior. So if we scale the graph, left end of the graph will go down, whereas the right end will go up. Now the question says in the second part, use the synthetic division to find the other two x-intercepts. In general, what happened is if the degree of the polynomial is 3, there are 3 x-intercepts. Okay, there are 3 x-intercepts. So we are asked to use the synthetic division, and then we are asked to find the other 2 intercepts. As I mentioned before, if we use the synthetic division using -1, the remainder will be 0, and we'll be able to reduce this polynomial to a lower degree there. So how does that work? Let's see. So let's begin with the synthetic division. So let's first do synthetic division. We are dividing with that -1. And then in order to perform the synthetic division, we write only the coefficients from there. Okay, from the polynomial, from this polynomial, we'll only write the coefficient. So there is 3 first. 3 is the coefficient for x cubed. Then for x squared, it's 8. For x, it is 3. And then we have a -2. And how we perform the synthetic division is we bring this 3 down, and then we multiply this -1 with 3. So -1 times 3 is a -3. And then if we add, we have to add now, that's a 5. Again, we multiply these two, -1 times 5, that's a -5, and we add them together, okay? -3 plus a -5, that will be -2. We repeat the process. We multiply -1 with -2, that's a +2. And we add these two, that will be 0. And as I mentioned, this is the remainder, okay? This is the remainder. So what is going on is now we can write our polynomial like this. P of x is equal to, see, if x equal to -1 is one of the zeros of the polynomial, then the factor will be x plus 1. So one factor will be x plus 1. And the other factor will be quadratic factor. This one here, this will give the quadratic factor, which will be 3x squared, then plus 5x minus 2. Okay, so that is the power of synthetic division. When you perform the synthetic division, you'll be able to write this cubic polynomial as a product of linear and quadratic. And you know that it is easy to factor this polynomial here. So now we can write this as x plus 1. Okay, if we factor 3x squared plus 5x minus 2, the factors are x plus 2 and 3x minus 1. X plus 2 and 3x minus 1. Okay. So once we do this, once we factor the polynomial completely, now we can analyze this. We want to find the other two x-intercepts or 0. Meaning of that is when you plug in those values, the polynomial should be 0. That means we can equate this polynomial to 0. So let x plus 1, x plus 2, 3x minus 1 equal to 0. And if we solve this, the way we solve is we equate each factor to 0. So if we do that, we get x equal to, from the first one, x equal to -1, which was already given, okay? And then from here, it will be -2. And from here, 3x minus 1 equal to 0. If 3x minus 1 equal to 0, x will be 1/3. So meaning of that is the x-intercepts occur at -1, -2, and 1/3. And we are asked to find other two intercepts. One is already given. So other two intercepts are, so other two intercepts are -2, 0 and the next one is 1/3 comma 0. Okay, -2 comma 0 and 1/3 comma 0. Meaning of that is if you plug in -2 into this function, the result will be 0. If you plug in 1/3 into this function, the result will be 0. So this is how we can use synthetic division to find the remaining zeros of the polynomial when one of the zeros is given. This concept is the exact same concept that we'll be using when we try to solve the polynomial equation. So later on in other example, we'll be solving the polynomial equation using the same concept. But also you can verify this work, the work that we have done here, using graphing utility. So you can always use your graphing tool, TI-84 calculator, or whatever you have with you, and then you can sketch the graph. Okay, you can sketch the graph. For example, I have the graph here. This is quite difficult to see. Let me do one thing. Let me move this graph here for a little bit and then make it a little big for you to see like that. Okay. You can see I said that the intercepts occur at -1. You can clearly see it occurs here at -1. Okay, where I'm pointing. It also occurs at -2. This is -2. And then it also occurs at 1/3. So this value, which is here, is less than 1. So it should be 1/3 there because this is 1. Okay, this is 1. So that should be 1/3. So you can clearly see we can always, verify our work using the graphs because graphs are a very powerful tool to, understand any function. And also in the first part, when we describe the end behavior, we say that the left end of the graph will go down. You can see here the left end going down and the right end of the graph will go up as mentioned here. Okay. Okay, let's move on to next one now. So as I mentioned before, we are going to solve the polynomial equation here. So here we have a polynomial equation of degree 3 that we are asked to solve. Use the given root to help in finding the remaining root of the equation. So here is the polynomial equation. As you can see, this is our, let me use a color here. This is our equation. And they have given that one of the roots of this equation is -1. This is one root. Okay, one of the roots of this equation is -1. And we have to find the other roots. In general, the number of roots of a polynomial equation is equal to the degree of the polynomial equation. So this one is a polynomial equation of degree 3. That means it has 3 roots. Out of those 3 roots, one of them is -1. Okay, one of them is -1. So we have to find the other roots. So same process as before. What we do is we do the synthetic division using -1. And you'll see that the value of the remainder will be 0. And we'll use that to rewrite this equation. So let's begin with synthetic division. Synthetic division. So if we perform the synthetic division with -1, let's see, we do -1. We start with the coefficient of cube, okay, highest degree, that's a 4. We don't have x squared here. That means we have 0x squared. So we have to write that one too, 0x squared. Then we go to x, coefficient of x is -3. And then we go to the constant of the number, that's a 1. Okay. Now to perform the synthetic division, we bring this 4 down. And then we multiply -1 with the 4. So that becomes -4. And we add these two numbers. That's a -4. Again, we multiply -1 with this -4. -1 times -4 is a +4. Then we add these two numbers, which will be 1. Next, we multiply -1 with +1, which is a -1. And then we add these two to get a 0. We must get a 0 because -1 is the root of the equation. That's why when you divide, we get that. So this one will help you to write this polynomial equation in factored form. Now what you'll see here is because -1 is the root, so the factor will be x plus 1. Sorry about that. Okay, x plus 1. And then this cubic can be written as a product of linear and quadratic. So this one will give you the quadratic, which is 4x squared minus 4x plus 1 equal to 0. And then we can factor this quadratic. So let's do that. So it will be x plus 1 times, that will be 2x minus 1 times 2x minus 1 equal to 0. Because if you FOIL 2x minus 1 and 2x minus 1, we get 4x squared minus 4x plus 1. So that's why when you factor that, we get this. So we factor that trinomial and we get this one. Now, finally, because we want to find the roots, so let me write here. Let me rewrite that. X plus 1, 2x minus 1, 2x minus 1 equal to 0. So from here, if we try to solve this, we equate each factor to 0. So what we get is, we get x equal to, the first root will be, when x plus 1 is equal to 0, x will be equal to negative 1. When 2x minus 1 is equal to 0, x equal to positive half. And same thing here, 2x minus 1 equal to 0, meaning x equal to half. So we get 3 zeros here, negative 1, 1 over 2, and 1 over 2. Negative 1 was already given, and we are asked to find the remaining roots. So remaining roots are half and half. So remaining roots are half and half. Or sometimes we say that remaining roots, or the root half, has a multiplicity of 2. That means it occurs twice. That is the meaning of that. Okay, so this is how we can solve the polynomial equation of degree 3. In next example, we are going to see how we can solve the polynomial equation of degree 4 using the very similar concept. And here is that example. Use the given root to help in finding the remaining roots of the equation. And here is the 4th degree equation given. This is the 4th degree equation. Meaning of that is, we'll have 4 roots, and one of the root is already given. This is one of the roots. This is the root. Okay, so now what we are going to do is, we are going to solve this one and then find the remaining roots. Let's see how we can do that. It will definitely take a little bit of time because this is the 4th degree, but the root is 1. So we are going to begin with that synthetic division, because synthetic division is very powerful in reducing that 4th degree polynomial to the factored form. So let's begin with synthetic division. Synthetic division. And we are performing the synthetic division, okay? We are performing the synthetic division with 1. So we start with that 1. And then we start with the 4th degree. For 4th degree, the coefficient is 1 because that is 1x4. We don't have x cubed, meaning we have 0x cubed. Then we have x squared, but negative 1x squared. Okay, then we have a negative 2x, and then we have a 2. Okay, now what we do is we bring that 1 down and we start multiplying. 1 times 1 is 1. We add here, 0 plus 1 is 1. We multiply these 2, so that's also 1. And if we add again, that's a 0. And then when we multiply again, that will be 0 again. And when we add negative 2, if we multiply, that is again negative 2. And when you add, 0. Okay. So that means this equation is reduced to this one. So I can write reduced equation as a cubic equation. So let me write the reduced equation is a cubic equation. So we start with 1x cubed, okay? 1x cubed plus 1x squared, no x, and then minus 2. Minus 2 equal to 0. Now remember one thing, this is a fourth degree equation. It has 4 roots. One of the roots is already here. Now we reduce the equation to third degree equation. And this third degree equation has 3 roots. We have to find those 3 roots. And one technique of finding the roots is we can use this constant to determine the possible roots. So possible roots are the factors of -2. So what I'm saying is this. Possible roots are plus or minus 1 and plus or minus 2. Okay, so out of these 4, you should have at least one root. That's what we know. So how we can check this is we can start plugging in 1 into that equation, then -1, 2, or -2 until it satisfies the equation. Now let's try with x equal to 1. Okay, try with x equal to 1. And let's see what we get. If we plug in 1, that's 1 cubed, which is 1, plus, if you plug in 1 here, 1 squared is 1, and then minus 2 equal to 0. 1 plus 1, 2 minus 2 is 0. This is the true equation. That is true. That means the second root is also x equal to 1. So first root was 1, second root is also 1. So meaning of that is, let me write here at the side. So second root is also x is equal to 1. That means, again, if we do the synthetic division using this 1 to this equation, we'll be able to reduce that to quadratic equation, and we can easily solve quadratic equation. So let's do synthetic division again. Synthetic division. So divide by 1, and we are dividing this cubic. Okay, we have 1x cubed, 1x squared, no x, and then -2. So if we bring this 1 down and multiply with 1, that's a 1. So 1 plus 1 is a 2. 1 times 2 is a 2. 0 plus 2 now. 0 plus 2 is a 2. And then 1 times 2 is a 2. And when you add, that is 0, because we already proved that x equal to 1 is the solution to that equation. So this will give us the reduced equation again. So this implies reduced quadratic equation. Quadratic equation is this one, x squared plus 2x plus 2 equal to 0. And you can clearly see we cannot factor these 2. We cannot find 2 factors of 2 that will add up to 2. Meaning of that is we should solve this quadratic equation using quadratic formula. If you forget quadratic formula, for quick recap, this is the quadratic formula. X equal to -b plus or minus the square root of b squared minus 4ac all over 2a. And for this equation here, you can see we have 1x squared. That means a equal to 1. Bx, so b is equal to 2. And c is also equal to 2. We have all a, b, c's there. So now let's use that quadratic formula to find the remaining roots, because we already have the first root given. Here we got the second root. Let me also use that color there. There is the second root. Now we need 2 more roots. So to get 2 more roots, we are going to solve this quadratic equation using that quadratic formula. So let's see what we get by using that formula. Now, x is equal to -b. b is 2, so -2. -2 plus or minus the square root of b squared. B squared is 4 minus, okay, minus 4ac, 4 times 1 times 2, that's 8. Divided by 2a, 2 times a is 1, so that's a 2. So that means I can write this as x equal to -2 plus or minus. Now look here, 4 minus 8 is a -4. And the square root of -4 is a 2i. 2i divided by 2. And if we simplify this, we get x equal to -2 over 2. That's a -1. And then plus or minus 2i divided by 2 is a I. So that means here we got two values, -1 plus I and -1 minus I. Here we are asked to find the remaining roots. So now finally we can write our remaining roots here. Let me write here. Remaining roots are, okay, first root was given. Here we found the second root. Second root is x equal to 1. Okay, and then the third root, we get two roots here. Third root is -1 plus I. -1 plus I. And the next one is -1 minus I. -1 minus I. Okay, so this is how we can solve the the fourth degree polynomial equation. And remember, synthetic division is very powerful in reducing the equation from fourth degree here to a third degree, and then from third degree to a second degree or quadratic. And once you get to quadratic, you can easily solve using quadratic formula. So this is the basic idea on how we can solve the polynomial equation. So I hope you enjoyed the video where we explore the polynomial functions and equation. You guys have a wonderful day, and I'll see you next time.